All right. Yesterday was so much fun, we're deciding to pick up the next lesson. So in the unit of transformations, there are things called translations, which are movements generally from side to side. And these movements are additive, or we do it by adding to the x and y. So now we are going to be taking a look at multiplicative transformations, and we're going to be multiplying. These are called reflections and stretches. So recall from last year, when we took a look at parabolas, y is equal to x squared, looks something like this. And if we reflected this about the x-axis, it became this, a downward opening parabola. Now that was under the case where a was equal to -1. So let me get over the definition and stop blabbing here. A reflection is a transformation where the graph of f of x is reflected about the x or y axis. In other words, it creates a mirror image about the x or y axis. Reflections are not said to change the shape, but rather they change the orientation of your graph. So for example, we have an upward opening parabola that might change it to a downward opening parabola. Or if we have a left-facing graph, if we're reflected about the y-axis, it might change it so it becomes a left-facing graph and might become a right-facing graph. So let's get started. Reflection and stretches summary. So, by the way, before we get started, perhaps I should write just a little bit here. So, last lesson, we've taken f of x and we changed it so it became y is equal to f of x, x minus h plus k. That was the horizontal and vertical shift, if you recall. Now, what we're going to do is we're going to add another parameter, and that parameter is a. So y is equal to a f x minus h plus k. Again, we can draw on our experience from last year to help us out. So let us start here by function. Y is equal to negative f of x. So really, y is equal to negative f of x. Here, a is equal to -1. So this parameter a, right here, is going to be equal to -1. We call this a reflection about the x-axis. And the mapping notation takes any point x, y on our parent function. So let the blue graph here be our parent function. And it changes it into each and every point. So point xy becomes point x negative y. So if the blue is our parent function, that's point 2, 4, and it becomes point 2, -4. Notice how it was only the y value that became negative. So when a is -1, or negative in general, we say it's a reflection about the x-axis. Now let's move on to something a little bit different. If y is equal to f of x is equal to y is equal to f of negative x. Now notice the negative is attached to the x, not in front of the f. This is a reflection about the y-axis. So it takes point xy and moves it to point -x, y. So here, let's suppose the blue is our parent function here. This will be point -3, -1. And if we reflect this about the y-axis, it becomes point 3, -1. The x's, we multiplied the x's by -1, or in other words, we switched the signs, but the y value stayed the same. All right. So here, now we're going to have to change up our dynamic a little bit here, and we're going to make it b is equal to -1. Now, at the end of this table, I will probably expand on this a little bit. Now, let's move on. We're going to vertically stretch about the x-axis by a factor of the absolute value of a. Oh my God. So this is kind of getting complicated now. So when a has a value not equal to 1, we vertically stretch it. So here, in this example, a is equal to 2. We say that we vertically, or the graph is vertically stretched by a factor of 2. So here, what does it mean to stretch? So here, a is equal to 2 in this example right here. Ooh, that was bad. A is equal to 2. So what happens? We are saying simply we multiply the y values by a. If a is 2, we take point x comma y. In this specific example, now becomes point x 2y. So this point was point 2, 4. When we stretch it upwards by a factor of 2, now stretch, if you notice, think this point is being held down. You're putting your foot down along the x-axis and you're pulling the graph up. How much are you pulling it up? Well, you're pulling it up by twice the amount. Okay? Now, if you notice, now we attach another parameter b in front of the x. Oh, this is called a horizontal stretch by a factor about the y-axis by a factor of 1 over b. Now, here, the blue is the parent function again. Now, the purple, I'm just going to say, is going to be the transformed function. Here, I said my example, b is 2, right? So, if I horizontally stretch this, I'm going to horizontally stretch it by a factor of 1/2. We do have other words for it that might make more sense. But my point xy becomes point, now how did that work? Oh yeah, x divided by b, x over 2 comma y. Very simply, putting it together in a very complex task here is that the range stays the same. That is, the y values stay the same. It's only the x's that change. Well, how did the x's change? So I'm going to take this, and I'm just going to say this up here was 0.24. I ask myself, how did this point change? Well, this point got transformed into, since b was 2, it got transformed into 1, 4. In other words, we took the x value 2 and we divided it by 2. So we say that this is stretched about the y-axis by a factor of 2. That doesn't seem to make sense. Sorry, stretched by about the y-axis by a factor of 1/2. We can change the language. And we can say it's been compressed by a factor of 2. So before we move on, I'm just going to maybe say we started off with last lesson y is equal to f of x, and now we've moved into, right, last lesson was y is equal to f x minus h plus k, which is the horizontal and vertical shifts. And now what we're doing here, by the way, h and k, very simple. H was horizontal, k was vertical. Each letter stood for only one thing. Today, though, I'm saying we are moving into y is equal to a f b of x. Now, what's so strange about this is that the a, if it's negative, can reflect. A can also vertically stretch. So it's a reflection about the x-axis. B affects things horizontally. So it compresses or stretches about the y-axis, but it can also reflect about the y-axis as well. Okay? So let's get moving on, shall we? All right. Let's work on this example. Example, we're going to do a reflection about the x-axis and y-axis. Given the graph, y is equal to f of x, we're going to denote the domain and the range. So let's start off with the domain and range. So domain and range is really important here. So it really describes the x and y value. I'm just going to use set notation. So the domain and range here So my domain goes from -2 to 4. So I'm just going to use interval notation. I like interval notation whenever I can. It's simple, it communicates the idea. Range goes from 0 to 3. Okay, that's of my regular function f of x as it appears. So I am going to sketch the graph of the transformed graphs. Okay, so A and B, I'm going to see how the graphs change. I'm going to write the mapping notation in point x, y. I'm going to describe it in words. Wow, this is a heavy question. And note the domain and range of the transformed graph. So I'm going to start off with A. I'm going to use the color red for A. So we're going to sketch the graph, the transformed graph. So here, now this is f of x. I'm going to draw this g of x, and this g of x is going to be negative f of x. So I'm just going to spot out right away y is equal to, I'm just going to write this to help me out, bx, right? Okay. This is what we're really talking about, and in next lesson we'll try to combine everything all at once and see how that goes. But anyways, what I see here is a is equal to -1. The negative appeared in front of the x. So what does that mean? It means it is a reflection about the x-axis. So I actually think that this third point is most important. So I'm just going to say it's a reflection about x-axis. So this point, now the mapping notation is also important. So I'm just going to take point, I start off with point x, y, and I transform that. Now I'm going to switch to red. It should come to point, if I reflect about the x-axis, x comma -y. So this was -2, 3. This goes down to -2, -3, all the way down there. This point was 2, 1, comes point to -1. This was 4, 1, it should come down to point 4, -1. Simply there's my function. You notice how I didn't put arrows on? Really important. So I sketched the graph, check. I've written the mapping notation, check. I've described it in words, check. I denote the domain and range. Well, the domain and range for the new function, the domain remains unchanged because the transformation just happened to the y's. How did the y's change? The y's were simply multiplied by -1. There you have it.